All right, so this is like our first video in this like online lectures or so. All right, so the topic now is a certain procedure called the one-handle attachment that takes as input a surface sigma and it will output some other surface that I am denoting here as hashtag D1, D2 sigma. And how does this work? So roughly speaking, it just takes out two disks that are in sigma, and so as we do this leaves out only just the boundary of the circles, and these two boundaries, these two S1s, are then identified by gluing in a cylinder. All right, and basically we yield this picture. So how do we formalize this? All right, so I start with a surface sigma. Here I'm requiring that it's oriented. This is not necessary, so we will do this later for non-orientable surfaces. But sort of this simplifies the construction in the beginning. So we'll see why later. And orientability basically means, right, that sigma locally looks like R2, so I can just choose an orientation as a vector space. So I say, okay, this vector is the first, this vector is the second. And orientability tells me that once I've made this choice is consistent all across the surface. All right, so this we have as a given. And then additionally, we've chosen two disks, D1 and D2. They are disjoint from one another. They're subspaces of sigma. And as I do this, the orientation gives me the following. So if I take the disk D2, for instance, let's say, and I zoom in, the orientation of sigma restricts the orientation of the disk. So here I have it again, first vector, second vector. And in particular, this tells me that I can orient the surface, not the surface, the boundary of D2 by following the boundary orientation, which basically means like, yeah, just turn along the boundary, basically going from 1 to 2. So the same is true for D2, and I've marked this as such by an arrow here. All right, so now what do we do? So we take the surface sigma, we remove the interior of D1 and D2, and we glue a cylinder, and this cylinder, I write it explicitly as partial D1 times 0, 1, right? Because partial D1 is basically homeomorphic to S1. Now, what we have to do left is say how this cylinder is glued here. So partial of D1 inside of sigma is almost immediately identified with partial D1 times 0 by just taking essentially the identity, right? So this is like the left-hand side of the cylinder, and the right-hand side of the cylinder is a bit more tricky. So I have to tell you how do we identify partial D2 inside of sigma with partial D1 times 1, right? And this is not automatic. This we have to choose some homeomorphism. And to see what's a good choice, let's look at the picture. So let's see. So for instance, if I take this point in D1 that I marked in red and I follow it around roughly in the cylinder, I will end up here. And if I take this point, I will end up here. Similarly, if I take the whole S1 and I just push it up, sort of following the cylinder, here we see it, its copy. Maybe this is like partial D1 times some key. And I keep pushing it. And what we see is that as we approach partial of D2, the orientation that we've inherited from partial D1 is opposite to orientation in partial D2. So that tells me that if I want to identify partial D2 with partial D1 times 1, what I have to choose to make this picture rigorous is to choose an orientation reversing homeomorphism phi. Okay, so this is a choice we make. I didn't write it here, but indeed this construction does depend on phi a priori. And okay, that's it. That's a construction, and we call this the one-handle attachment to, let's say, a one-handle attachment to sigma along D1 and D2. All right. Very good. So now the first preliminary lemma we can show about this is that this construction we've just defined is equivalent up to homeomorphism to this other possibly simplified construction, which is you take sigma, you remove the inside of the disks, and now instead of gluing the cylinder, we directly just identify partial D1 with partial D2 by this homeo phi that is the same as the phi before. Okay, why are these two things equivalent? So here's the picture. Let me start maybe by analyzing the left-hand side. So the left-hand side has basically two pieces. One of them is sigma minus the disks, right? and the other piece is the cylinder itself. And here it's shown how these are glued, right? So we've said on this side we glue the cylinder to partial d1 by the identity, and here we glue it to partial d2 by phi. Now, the right-hand side, the new surface, is a bit different. So we want to decompose it again into two pieces. One of them should play the role of the cylinder, and the other one should play the role of the rest of the surface. So the way to construct the cylinder, so you should first observe, right, that partial d1 is directly identified with partial d2, so there's no cylinder at all. So to play its role, we basically take a slightly bigger disk surrounding d2, and the annulus between d2 tilde, the bigger disk, and d2, the smaller disk, it's an annulus, and in particular, it's isomorphic to the cylinder. So we'll try to identify them by this map that I call here big phi. And now the claim is that the rest of the surface, so sigma minus the inside of d1 minus d2 tilde interior, so I've also removed this green part, it's in fact homomorphic to the surface minus the two original disks. Okay, so if I construct these two identifications, big phi and psi, and I define them correctly, then they will glue to a global homeomorphism between these two surfaces. All right, so let's look first, I guess, let me see, at the first one, at psi. And the way I'm going to do it is basically I'm going to define the inverse of psi. It's slightly, well, it doesn't make a difference, but it's slightly easier, and it's what I wrote. So, all right, so what is the picture? So what we do is we pick a slightly bigger ball d2 tilde tilde, and sort of what I can do is I can take d2 itself. This was a disk, I said, so we identify it directly with the disk. I identify d2 tilde with the disk with at radius 1 plus delta, and d2 tilde tilde with the disk of radius 1 plus 2 delta, right? And now once I've done this, what is the claim? Well, basically you can readily observe that d2 tilde tilde minus d2, so the big annulus, it's homeomorphic to the smaller annulus, and they're homeomorphic by a homeomorphism that in fact fixes d2 tilde tilde. So that means that basically in this picture, I can map from here to here by basically taking this annulus, this part, and contracting it a bit, which is what I'm doing here. I contract the big annulus to the smaller one. All right, and because this transformation fixes the boundary of d2 tilde tilde, then I can just extend this map by the identity everywhere else. So I will have a globally defined homeomorphism between these two pieces. The second step then is actually easy. So to define big psi, all I have to do is say, well, okay, so this annulus here is yet again identified with partial d2 times 1 to 1 plus delta, right? So this is already this annulus is already in a cylindrical form, and I identified with the other cylinder by basically, well, partial d2 to partial d1, they're identified by phi, or phi inverse in this case, and the radius part, they're just identified by rescaling and shifting. So that's it. That's the whole construction, and basically I leave as an exercise showing that these two definitions glue nicely. Right, and sort of there's a little subtlety in what I just did, which is that sure, sort of by hypothesis, we know that d2 is in fact homeomorphic to the disk of radius 1. But actually showing that you have like nice neighborhoods like this, it's kind of like, I mean, you have to do this. It takes some work. When we're talking about smooth objects, so a smooth surface and a smooth disk, then it's easy. But in this course that we're always talking about topological stuff, showing this is actually a bit more tricky. But okay, this is a detail I'm gonna jump over. Hopefully you believe this is true. And something that is interesting about this construction, the one handle attachment, is that there's one particular case that is of interest, which is that is what we call the connected sum. So at no point did I say that sigma was connected. So let's assume that for a second that sigma is in fact the union of two path components, sigma 1 and sigma 2, and each disk is in one of the components, like in the picture. Then doing the one handle attachment identifies basically the boundary of d1 here to the boundary of d2 here, and now the two surfaces have been joined, right, by this bridge, by this tube, and the resulting surface we call the connected sum, and you should be able to show readily that the connected sum is connected, path connected. All right, so that's a little exercise, and we denote it like this. All right. All right, so let's prove some of the properties that the one handle attachment has. The first one, of course, is that the one, I mean, like the resulting thing should be a surface. This I claimed before, right? And I'm not gonna do all the details. This is an exercise for you as well. You should really do it. Sort of, it's probably enlightening. But I'm gonna give you the idea, which is sort of let's drawn here. So let's say I have D1 here, and I have D2. And we can assume, right, that basically D1 has a, I mean, it looks like basically the unit uh, disk in R2, and D2 looks like the unit disk in R2 as well. So what we can do is we can take a piece of the boundary here that is identified with another piece here and find a little neighborhood. And this little neighborhood looks like what? So basically you should be able to take this piece of the boundary of D1 to R inside R2, and this part should be taken to the upper half plane, and in particular should be taken to, well, let's say to D2 intersected with the upper half plane. This should be quite easy because you should be able to basically to parameterize this part of the curve explicitly and therefore map it immediately to R and so on. The same is true here. And once these two pieces look like two half disks, then, well, you're just gluing, right? So you obtain an actual disk, which is like the usual neighborhood, like the usually Euclidean neighborhood you want for a surface. All right, so that is the exercise. Let's go on to the next lemma, which says the following. So here in the notation, when we define this one handle attachment, I didn't even introduce the homeomorphism phi, even though I probably should have. And the reason for this is that, in fact, phi is not important. So if I change phi by some other orientation reversing homeomorphism, then the resulting surface will be homeomorphic to the original one. So sort of up to homeo, this is not relevant. And how does this work? So the fundamental claim in which this relies is the following. So if I have two maps, phi 0 and phi 2, that they are like orientation reversing homeos of partial D1 and partial D2, then it turns out that these two maps are in fact homotopic, and they are not homotopic through random maps, but through orientation reversing homeomorphisms. All right, and in fact the same is true for orientation preserving. We'll see this in the proof. So how does this claim work? So we've already done very similar things before, so let me go quickly through it. So the first thing we can do is I can replace phi 0. I can sort of homotope phi 0 through orientation reversing homeos to some phi 1, such that phi 1 and phi 2 take the same value as at 1. And how do we do this? Well, we simply rotate phi 0, right? We take phi 0 and we multiply it basically by a complex number. For at t equal to 0, this number is just 1, so I get this. I start at phi 0, and then I move all the way to this number that basically makes me start at phi 0, phi 2 of 1. All right, so this is, we've done this before many times. The second part is also standard. So what we do is, once we have phi 1 and phi 2, these start at the same point. What I can do is I can lift the map. So this is actually the expression. So alpha 1 is a lift of phi 1, and alpha 2 is a lift of phi 2. And now phi 1 and phi 2 are maps basically of the interval into R, and they have the same endpoints. And we have shown before that maps of the interval into R with the same endpoints are relative to the endpoints, and this is just done by doing the linear interpolation, as we see here. But what you should observe, and this is the key fact, is that linearly interpolating, in fact, it's not just a homotopy, but it's a homotopy of orientation reversing homeomorphisms. And the reason for this is that both alpha 1 and alpha 2, I mean, being a homeo basically means that in this case you're like strictly decreasing. So when you do the linear interpolation, you're still strictly decreasing. All right. So that is one thing. So that proves this claim that that any two orientation reversing homeomorphisms are homotopic. And now what we can do is conclude the proof in the following way. So let me explain this as follows. So let's suppose we have two different orientation reversing homeos, phi 0 and phi 1. So I didn't know the corresponding surfaces like this to make clear the distinction. And now I want to find the homeomorphism between them. How do I do this? So in the first piece, in the piece corresponding to the surface minus the disks, I just use the identity. And now what I do is I define a homeomorphism between the cylindrical parts that does the job. And what should this be? So let's look how this works. So if I look at partial d1 times 1, right? So this corresponds to partial d2, right? Through the map phi 0. Now I map through the identity to partial d2, and now I map back to partial d1 times 1 by phi 1 minus, like the inverse of phi 1. So what that tells me is that I'm forced essentially to put here some map. So basically the cylinder is like the interval part is identified just directly, but in this part we take basically a homeo of partial d1 that it starts as the identity in 0, and then it moves to phi 0 composed with phi 1 inverse. This should be inverse. And this is exactly what you have to put in order so that everything glues with the other piece. All right, so you should check that this is indeed that this works. And having shown that basically the homeomorphism phi doesn't matter, our next goal is proving that the choice of d1 and d2 doesn't matter. And this is not quite true, so it depends, but basically it depends on very little, as we will see next. So then the definitions we need are the following. So we say that a map from a topological space A to a topological space B is an embedding if F is basically, it's a homeomorphism between A, the domain, and its image, f of A. All right? So for instance, the maps we were looking at before, like basically the inclusions of D1 and D2 are embeddings of the disk into our surface. Now, what we're basically saying is that we want to see how much does this construction depend on how D1, how these disks sit inside of sigma. So what we have to look is like what happens when I change the embedding of these embeddings of the disk. So this is the relevant definition in this case. So we say that two embeddings of a topological space A into B are isotopic if they're homotopic through embeddings, right? So not all the isotopies will be through embeddings, and so this is what we additionally require. And a slightly stronger notion is that two embeddings are ambient isotopic if there is an homotopy of the target, so of B, such that it moves F. So this homotopy starts as the identity. It's a homotopy of homeomorphisms, and G1 composed with F0 is F1. So that means that basically I can do a family of homeomorphisms of V that moves F0 to F1. All right. So what is the proposition now? So we say that, let's start again. So sigma is a path connected oriented surface. Then any two orientation preserving embeddings F0, F1, right? So these are like D1, D1 and some other map D1. Yeah, they are in fact ambient isotopic, and from this we will deduce that in fact the choice of D1 and the choice of D2 doesn't matter up to ambient isotopy. All right, so this statement is actually sort of hard to prove. Formalizing this in the world of like differentiable surfaces and so on is not so bad. I mean, it's actually, I mean, sort of the idea of the proof basically goes in the direction, but for the continuous case in which we are in the topological case where these maps are just continuous maps, then this is actually slightly trickier to formalize. So I will just provide a sketch, and well, I mean, it's good enough for this course, so that you're just aware of the idea. So how does this work? So the first observation is the following. So if I start with any embedding of D2 into sigma, then it is possible to homotope F to some other embedding f1 such that f1 has like a arbitrarily small image. And what is the idea? Well, you take f, you precompose by phi t, where phi t is just a map of the disk to itself that basically just contracts, right? So phi 0 is its identity, and phi 1 has contracted everything to the origin. But so indeed, phi 1 is not a homeomorphism, but all the other maps are. So this tells us that for t different to 1, f of t is an embedding. And for t very, very, very close to 1, the image of ft is actually a very small disk, because we've contracted the disk itself to a very small part, and then when we map it by f, it will still be small. What one can then show is that in fact you can use an ambient isotopy in sigma to do exactly this process. So you can find a homeomorphism of sigma that is the identity outside of the image of D2, and it contracts the inside of D2 a lot. Yeah, well, okay, let me be careful. So it's a map that is like the identity outside a small neighborhood of f of D2, and then it compresses D2 a lot. And this is very similar to the construction, to some of the constructions we've done before, like for instance here. So that's left as a little exercise. Try to convince yourself this is true. And now, once we are in this situation where both f0 and f1 have been homotoped to embeddings with very small image, I will still denote them by f0 and f1 for simplicity. So now that they're really, really small, what I can do is I take the center one of the disks, I take the other, I connect them by a path. This follows from path connectedness. I call this path new. And if these balls are really, really small, then some small neighborhood U of nu will contain both. And now what you can readily imagine, I mean, you can try to write a formula for this, is that you can find an isotopy that pushes this part of the annulus to the other part while keeping the boundary of this little box fixed. So this will immediately be an ambient isotopy that is transporting this ball to this ball. All right. So as I said, this is in the differentiable world. This is not hard to show. You can just use this with using vector fields and so on and flows. But to do this in the topological world is a bit more involved, and meaning in either case you have to understand a bit what the diffeomorphisms of D2 are and what the homeomorphisms of D2 are, and this is a bit beyond the scope of this course. All right, so that's roughly the idea. Some good news though is that this proposition, well, okay, let's give the corollary. So the corollary is that because we can move D1 and D2 freely around sigma, then this surface, the one handle attachment, it only depends up to homeo on D1 and D2 up to isotopy. So if I glue my cylinder if I'm attaching a cylinder and I move one of the disks, then whatever I get is still the same surface up to homeo. We leave this to the reader. This is the same as before, as one of the first lemmas. That's the first lemma we showed today. But in any case, I mean, this corollary, it will follow, in fact, from the classification of surfaces we'll do later. So even though this proposition we haven't given a formal proof, it will follow from the combinatorial arguments about planar representations we'll do a bit later. But it's good that you have like sort of in mind that this is true and why is it true and so on. All right, so now what we're going to do is, I mean, we spent some time introducing planar representations, and they are like the key ingredient we need to prove the classification of surfaces later on. So it's worth understanding how they change as we attach handles. All right, so suppose we have some surface sigma, which is oriented and path connected. And suppose we have some planar representation of sigma, right? So this is some polygon whose boundary is a bunch of edges that are oriented. Then they are labeled by these symbols Aij. And these symbols Aij tell me, and their orientations tell me how to glue one, like how to identify edges. So okay, let's assume basically like the edges are presented in this way by this word. So this means, okay, first we do this, edge oriented given by this one or the plus one or minus one, and all the way up to this. So here we have n edges. All right, so we have this planar representation, and now what this says is that the one handle attachment of sigma, here I'm not putting d1 and d2 anymore because as we've discussed, it's not important really what they are up to isotopy. Then yeah, so the one handle attachment of sigma has also a planar representation, and this planar representation is described by the word, well, the same word, and then you attach to it at the end the commutator of b and c, some new two symbols. So how do you do this? So all right, so let's draw here the planar representation of sigma. So I'm drawing it around here in black, and here's the inside of the polygon. Now, what I'm doing, right, is I want to attach a one handle, so I have to tell you where D1 and D2 are, just for concreteness. And because I can choose them wherever I want, I'm gonna choose D1 here and D2 here, okay? And now, look, now I'm drawing this arrow this arrow denotes sort of the orientation the orientations that tell me how to glue, right? So we said the boundary of the one has to be attached to the boundary of the two by a orientation reversing thing. So that means that if I orient this one in like counterclockwise order, this one has to be counterclockwise. This has to be clockwise. So that's exactly what this means. And because I'm going to identify them, I label them both as B. And now what we can do is, this circle, right, is identified with the circle. So that means that this vertex is also somewhere here, let's say here. And what I do is I just pick some curve connecting these two copies of P. And I denote this curve by C, and I orient it this way just for simplicity. And now what happens? So now we can basically write this diagram in a slightly different way. So since I'm attaching the handle, what was this before a disk and this which was also a disk, now they are gone, right? Like now they're identified with one another. So what I can do, so this I can remove, this I can remove, and additionally I can cut along C and just remember how I glue. And what this yields is that it says, well, I can do AIN first, then I do B, as shown here, then I do C, then I do B but with the opposite orientation, and then I do C with the opposite orientation, and then I continue, I restart the word. And now we are done, right? Because, well, all these vertices are P again, this is the original word, and this is the commutator of P and C. So this is exactly the claim. So a nice corollary of this is that, well, if I start with S2, right? S2 basically is given by the planar representation that has no edges, as we said, and I attach to it G1 handles. And every time I attach a one handle, I'm adding a commutator like this. And we saw in the previous class that when you have G commutators of this form forming the planar representation, this is exactly sigma G, the surface of genus G. So this is a nice corollary that all these surfaces are just obtained from S2 by attaching handles successively. And in particular, recall that out of this planar representation, we could compute the fundamental group as this. All right. Let us do instead a slightly different case. So now we have sigma. We don't assume it's path component, it's path connected. So now let's say assume instead it has two path components, sigma 1 and sigma 2. And each one of them, it's a connected path connected surface. So I present it as a planar representation. The first one with word W1 and the second one with word W2. Recall that we're still assuming that sigma is oriented. Okay. We haven't reached the non-orientable case yet. So what the lemma says is, like, if I have sigma 1 and sigma 2 and I do the connected sum, then this is a connected surface and it has a planar representation, and it's in fact given by just concatenating W2 with W1. And how do we see this? Well, okay, let's draw here the planar representation of sigma 1. Let's draw here the planar representation of sigma 2. As before, I choose the disks D1 and D2 sort of nicely, so touching the vertex P. that well, I mean, I call it P, but I mean, until I glue, these are not identified, right? Like these are in different components. And now when I remove this disk and I try to identify, what we see is that we've opened up the surface along this as one, and now they are glued. And when I glue, basically the planar representation is you do W1, and then you're here, but this is identified with this other part, so now you do W2. And this is equivalent to this. Probably I should have done it the other way around. So first I do W2 and then I do W1. It's completely equivalent. All right. And a nice corollary of this, of course, is that if I connect the surface with genus G and the surface with genus G prime, then I will get the surface with genus G plus G prime, right? Because if this one is basically G commutators and this one is G prime commutators, when I glue, I just get G plus G prime commutators. And a piece of notation that is useful, I mean, out of this computation is that when we say I have a path connected surface sigma and I do a one handle attachment, this is exactly the same as doing the surface and connect summing with T2. If you don't see this, I mean, you should see this immediately from the planar representation description we've given, but it's good that you think about it, try to formalize this a bit better. All right, and now we arrive to the non-orientable case, and now you'll see why sort of there's a little subtlety here. So, all right, suppose sigma is non-orientable, and imagine here we have an embedding of the disk, right? So this will be later play the role maybe of D1 or D2. So you have the disk, it's given by some map F, and of course D2 itself is orientable, right? So here D2 has an orientation, and what I can do is in its image put the same orientation, sort of the image orientation by F. Okay, so now we have this disk, even though sigma is not oriented, the disk is, and I've made a choice for this orientation. But because sigma is not oriented, I can find a loop that basically starts at the disk, it goes around or something, it comes back, but this neighborhood of this disk is a Mobius band, right? So it's a non-orientable thing. So what will happen is that if I take this disk, that you may imagine is very small, as we reasoned before, and I push it along nu, it will come back with the opposite orientation. And this tells me that it doesn't make a lot of sense to talk. I mean, of course, in Sigma, it doesn't make sense to talk about orientations, but this means that when I do this procedure of like deleting the inside and gluing, it doesn't make much sense to talk about what the orientation of this circle is. So that, as we'll see in a second, will give us a lot of flexibility. Let's in fact get to the proper formal statement. So let's suppose, for instance, that our surface sigma is given by a planar representation whose word describing the edges is W. Then here it is. Here's the planar representation. And now I'm gonna attempt to attach a handle. So what I do is I draw a disk here, which I'm gonna delete this interior. I draw a disk here and I'm gonna delete this interior. And I put some orientations here telling me how to glue these two circles, A and A. And what the construction we just did tells us is that this thing is exactly the same as gluing, but instead using the opposite orientation in one of the disks. All right, so what is the proof? The proof is basically the picture I made before, but let's do it for completeness. So since the surface is non-orientable, it means that in the planar representation, I can find some edge. I can find two edges that are labeled B, and both of them appear with the same orientation. So here is B, then the word goes on, blah 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 blah, blah, and then B reappears, and it's with the same orientation. As we saw in the previous class, this tells me that I can, if I take any path connecting these two edges, and these 2 points these are identified, so this point is the same as this point, then this path is in fact a loop, and it's a loop whose whose neighborhood is a Mobius band. So what you will see is that you start here with my disk with my circle with a certain orientation, we push it around, and then when it reappears, it appears with the opposite one. And this proves the claim. It proves that since gluing things along isotopic disks yields homomorphic surfaces, this means that it doesn't matter whether I attach the cylinder in this manner or this manner. So here I'm using again this idea that this like the embedding of the disk up to isotopy is not important. All right. So this has some nice, well, okay, it has some nice consequences. Give me a second, but let's just say first that for notation wise, one can also just say, well, for a non-orientable surface, attaching a one handle, which is what we call this process, either of these two because they're equivalent. Attaching a one handle is the same as you get your non-orientable surface and you connect some with T2. You should prove this. It should follow from the same reasoning as in the oriented case. And now a nice corollary of this is the following picture. So let's take RP2 and you connect some with itself G times. Okay, so you take G copies and you start putting bridges in between them. And the claim is that this surface that we get here is the same as this NG-1 that we defined. So okay, let's recall how this works. I mean, this statement just goes through like using induction over G. So okay, let's take NG, and if you recall, its planar representation was given by this word that I call WG here, right? Then what I do is I take WG-1. This is the word describing the surface NG-1. And now what I'm going to do to it is I'm going to attach one more RP2. The way in which I do it is, well, here I draw RP2. It has its planar representation that is basically like A squared, but now here I call it AG squared. And now I'm saying, well, I want to glue this circle to this circle here. We do the same thing. So this disk is not anymore here. This disk is not anymore here. So I can open up and I can open up. When I open up the RP2 minus the disk, I see this. When I open up NG-1, I see this. And now when I identify B with itself on each side, then we get exactly what we want. We get WG-1 and then twice AG, which is exactly the word describing NG, which was the claim. All right, so doing this connected sum with RP2, I mean, it's a nice operation and we give it a name. And this name is that we say that this is called attaching a cross cap to a surface sigma. And here sigma can be oriented or non-oriented. So this just means, yeah, whenever we connect some with RP2, we call it attaching a cross cap. And what is easy to see also already from this picture, but we are going to redo it again, is that attaching a cross cap has also a planar representation if sigma had one. And the word describing it is A squared W, where W is the word describing sigma. And the proof is almost immediate, so you just draw the planar representation of sigma here, right? This is given by W. And now what you're gonna do, right, is like you're gonna cut out something and then glue to RP2. But that's what will essentially happen is that basically the disk you're removing, it's equivalent to removing it out and identifying two halves of it by using A in this manner. Right, so this is something you should prove, and this obviously has as word W and then A twice. Well, here I did the other way around, but okay, doesn't matter. All right, so let's go to the last result of today. Let me see. Yeah, there we go. So it says that basically attaching a cross cap, that is, so connect summing with RP2 is equivalent to, well, if we do it twice, it's equivalent to attaching a one handle, that is connect summing with T2, as long as sigma is non-orientable. And it's a very nice picture, so let's see how it goes. All right, so let's suppose I have sigma, and its planar representation is given by some word W. So here it is. Now, when I connect some with T2 by what we proved before, then the planar representation is like W and then the commutator of A and B. Now, this is very useful, but it's kind of better to see it in the other following way more explicitly. So this is the original description, right? So here you have W, and here you explicitly show how you're gonna attach the one handle. Now, here we may use the non-orientability of sigma to basically take this circle here, move it along some path, and then it will return with the opposite orientation, right? And our claim is that these two things are equivalent, so we are still in the same surface, but now this has changed. And if I open up this, the planar representation I get is different. It's W and now AB, but now A appears with the same orientation and B is still with the opposite one. All right, so we've already gained something. And now what you may do is you pick an edge, and well, a new edge basically. Well, you connect by a line from the beginning of A to the beginning of one A to the beginning of the next A, and you cut there, and now you glue. And what do you see? So basically you do W first, then you do C, then you're gonna glue along A, and when you glue A, that basically means that you have to do C again. Now you have to do inverse of B, so you're here, and now you do inverse of B again. So you've done C, C, minus B, minus B. So you've essentially, you have the word W and then C squared and B minus 2. So that's exactly, well, the presentation of sigma connect sum twice with RP2 twice. So that's it. That's the end of the proof. And well, okay, this is like I don't know. You should try. I mean, this kind of proof is important. You should become familiar with this sort of proof by cutting and pasting because it will be sort of key when we prove the classification of surfaces a bit later. So the last observation, and this is the end of the video, is that you can show that attaching crosscaps and one handles is associative. So basically, at the end of the day, you can say I start with a surface and I attach to it, let's say G one handles and G prime crosscaps. And this is like a perfectly nice definition because it doesn't matter in which order you glue them. Even better, due to the previous lemma, you can substitute an even number of crosscaps by half the number of one handles. And basically, the way in which this works is that this relies essentially in this idea that attaching handles, and the same is true for attaching caps. It only depends up to, like, the choice of disks only matters up to isotopy. So you can just move them around and it doesn't matter at all. In any case, as I said, so this is a statement that we haven't really quite proven. We just given the idea. It will follow immediately from our classification of surfaces. All right, so that is the end. If you have any questions, please write them down in our discussion board on Blackboard, and I will try to like take a look at all of them, pick the ones that are most relevant and the most asked, and I will make maybe a video trying to solve your questions and so on. Yeah, take care.